and thank you for watching this video on Docker. This video is intended for intermediate to advanced developers without comprehensive knowledge of Docker. My name is David McHale. I'm a software engineer with over 6 years of experience shipping production code for nearly 24 companies. I'll be covering what Docker is, what it's typically used for, and how it can save you time and money. We'll also cover the differences between containers and images, the layering features that Docker provides, and how to build and run a to-do application using Docker. Docker is a platform that allows you to build and run any app, anywhere. It's come a long way in an incredibly short time and is now considered a standard way of solving one of the costliest aspects of software, deployment. Before Docker came along, the development pipeline typically involved combinations of various technologies for managing the movement of software, such as virtual machines, configuration management tools, package management systems, and complex webs of library dependencies. All the tools needed to be managed and maintained by specialist engineers, and most had their own unique ways of being configured. Docker has changed all of this, allowing different engineers involved in this process to effectively speak one language, making working together a breeze. Everything goes through a common pipeline to a single output that can be used on any target. There's no need to continue maintaining a bewildering array of tool configurations, such as Vagrant, Jenkins, and Chef, for development, test, and live environments. At the same time, there's no need to throw away your existing software stack if it works for you. You can package it up in a Docker container, as is, for others to consume. As a bonus, you can see how these containers were built, so if you need to dig into the details, you can. My goal is to expose you to some of the real-world challenges that Docker brings and to show you how they can be overcome. But first, we're going to go through a quick refresher on Docker itself. In the next video, I'll introduce you to Docker's architecture more deeply with the aid of some techniques that demonstrate its power. In this video, you're going to learn what Docker is, see why it's important, and start using it. Let's talk about the what and why of Docker. Before we get our hands dirty, we'll discuss Docker so that you understand its context, where the name Docker came from, and why we're using it at all. So what is Docker? To get an understanding of what Docker is, it's easier to start with a metaphor than a technical explanation. And the Docker metaphor is a powerful one. A docker was a laborer who moved commercial goods into and out of ships when they docked at ports. There were boxes and items of differing sizes and shapes, and experienced dockers were prized for their ability to fit goods into ships by hand in cost-effective ways. Hiring people to move stuff around wasn't cheap, but there was no alternative. This should sound familiar to anyone working in software. Much time and intellectual energy is spent getting metaphorically odd-shaped software into differently sized metaphorical ships full of other odd-shaped software so they can be sold to users or businesses elsewhere. Before Docker, deploying software to different environments required significant effort. Even if you weren't hand-running scripts to provision software on different machines, which plenty of people still do, you'd still have to wrestle with configuration management tools that manage state on what are increasingly fast-moving environments starved of resources. Even when these efforts were encapsulated in VMs, a lot of time was spent managing the deployment of these VMs, waiting for them to boot, and managing the overhead of resource use they created. With Docker, the configuration effort is separated from the resource management and the deployment effort is trivial. Run Docker run, and the environment's image is pulled down and ready to run, consuming fewer resources and contained so that it doesn't interfere with other environments. You don't need to worry about whether your container is going to be shipped to a Red Hat machine, an Ubuntu machine, or a CentOS VM image. As long as it has Docker on it, it'll be good to go. What is Docker good for? Some crucial practical questions arise. Why would you use Docker, and for what? The short answer to the why is that for a modicum of effort, Docker can save your business a lot of money very quickly. Let's dive into just a few of the ways Docker can benefit us in real working contexts. Number one, it outperforms virtual machines. Docker can be used to replace virtual machines in many situations. If you only care about the application, not the operating system, Docker can replace the VM, and you can leave worrying about the OS to someone else. Not only is Docker quicker than a VM to spin up, it's more lightweight to move around, and due to its layered file system, you can more easily and quickly share your changes with others. It's also firmly rooted in the command line and is highly scriptable. Number two, It assists in rapidly prototyping software. If you want to quickly experiment with software without either disrupting your existing setup or going through the hassle of provisioning a VM, Docker can give you a sandbox environment in milliseconds. The liberating effect of this is difficult to grasp until you experience it for yourself. Number 3, it simplifies packaging software. Because a Docker image has effectively no dependencies for a Linux user, it's a great way to package software. You can build your image and be sure that it can run on any modern Linux machine. Think Java without the need for a JVM. Number 4, it encourages a microservices architecture. Docker facilitates the decomposition of a complex system to a series of composable parts, which allows you to reason about your services in a more discrete way. This can allow you to restructure your software to make its parts more manageable and pluggable without affecting the whole. Number 5, it's a powerful tool for modeling networks. Because you can spin up hundreds, even thousands, of isolated containers on one machine, modeling a network is a breeze. This can be great for testing real-world scenarios without breaking the bank. Number 6, it enables full-stack productivity when offline. Because you can bundle all the parts of your system into Docker containers, you can orchestrate these to run on your laptop and work on the move, even when you're offline. Number 7, it reduces debugger overhead. Complex negotiations between different teams about software delivered is a commonplace within the industry. I've personally experienced countless discussions about broken libraries, problematic dependencies, updates applied incorrectly or in the wrong order or not performed at all, unreproducible bugs, and so on. It's likely you have too. Docker allows you to state clearly, even in script form, the steps for debugging a problem on a system with known properties, making bug and environment reproduction a much simpler affair, and one normally separated from the host environment provided. Number 8, it serves as documentation for software dependencies and touchpoints. By building your images in a structured way, ready to be moved to different environments, Docker forces you to document your software dependencies explicitly from a base starting point. Even if you decide not to use Docker everywhere, this documentation can help you install your software in other places. Number 9, it helps enable continuous delivery. Continuous delivery, or CD, is a paradigm for software delivery based on a pipeline that rebuilds the system on every change and then delivers to production, or live, through an automated or partly automated process. Because you can control the build environment state more exactly, Docker builds are more reproducible and replicable than traditional software building methods. This makes implementing CD much easier. Standard CD techniques, such as blue-green deployment, where live and last deployments are maintained on live, and Phoenix deployments, where whole systems are rebuilt on each release, are made trivial by implementing a reproducible Docker-centric build process. Now you know a little bit about how Docker can help you. Before we dive into a real-world example, let's cover a few of the key concepts of Docker. So, what are those key core concepts? It's useful to get the concepts of images, containers, and layers clear in your mind before you start running Docker commands. An image is a collection of file system layers and some metadata. Taken together, they can be spun up as Docker containers. A layer is a collection of changes to files. The differences between v1 and v2 of an application would be stored in layers. A container is a running instance of an image. You can have multiple containers running from the same image. In short, containers are running systems defined by images. These images are made up of one or more layers or sets of diffs, plus some metadata for Docker. Let's talk about some of the core Docker commands. We'll turn images into containers, change them, and add layers to new images that we'll then commit. Don't worry if all of this sounds confusing. By the end of this video, it'll all be much clearer. So let's discuss the key Docker commands. Docker's central function is to build, ship, and run software in any location that has Docker. To the end user, Docker is a command line program that they run. Like Git or any other source control tool, this program has subcommands that perform different operations. The principal Docker subcommands you'll use on your host are build, run, commit, and tag. Docker build will start the process of building a Docker image. Docker run will run a Docker image as a container. Docker commit will commit a Docker container as an image, and Docker tag will tag a Docker image for future reference. So, what are images and containers? If you're unfamiliar with Docker, this may be the first time you've come across the words container and image in this context. They're probably the most important concepts in Docker, so it's worth spending a bit of time to make sure the difference is clear. One way to look at images and containers is to see them as analogous to programs and processes. In the same way a process can be seen as an application being executed, a Docker container can be viewed as a Docker image in execution. If you're familiar with object-oriented principles, another way to look at images and containers is to view images as classes and containers as objects. In the same way that objects are concrete instances of classes, containers are instances of images. You can create multiple containers from a single image, and they are all isolated from one another in the same way objects are. Whatever you change in the object, it won't affect the class definition. They're fundamentally different things. So how can we build a Docker application? We're going to get our hands dirty now by building a simple to-do application, to-do app, image with Docker. In the process, you'll see some key Docker features like Docker files, image reuse, port exposure, and build automation. In the next few minutes, you'll learn how to create a Docker image using a Docker file, how to tag a Docker image for easy reference, and how to run your new Docker image. A to-do app is one that helps you keep track of things you want to get done. The app we build will store and display short strings of information that can be marked as done, presented in a simple web interface. The details of the application are unimportant. I'm going to demonstrate that from the single short Docker file we're about to write together, you can reliably build, run, stop, and start an application in the same way on both your host and mine without needing to worry about application installations or dependencies. This is a key part of what Docker offers: reliably reproduced and easily managed and shared development environments. This means no more complex or ambiguous installation instructions to follow and potentially get lost in. This to-do application will come up quite a few times, and it's great to play with and demonstrate to others, so I recommend familiarizing yourself with it. Let's discuss the ways you can create a new Docker image. There are 4 standard ways to create Docker images. The first is by hand. You can fire up a container with Docker run and input the commands to create your image on the command line. You can create a new image once you're done with Docker commit. The second is through a Docker file. You can build from a known base image and specify the build with a limited set of simple commands. The third is with a Docker file and a configuration management or CM tool. It's the same as a Docker file, but you hand over control of the build to a more sophisticated configuration management tool. Last, you can start with an empty image and import a tar file with the required files for your image. The first method, by hand, is fine if you're doing proofs of concept to see whether your installation process works. At the same time, you should keep notes about the steps you're taking so that you can return to the same point if you need to. At some point, you're going to want to define the steps for creating your image. This is the Docker file option, and the one we'll be using for the to-do app. For more complex builds, you may want to go for the third option, particularly when the Docker file features aren't sophisticated enough for your image's needs. The final option builds from a null image by overlaying the set of files required to run the image. This is useful if you want to import a set of self-contained files created elsewhere, but this method is rarely seen in mainstream use. We'll look at the Docker file method now, and I'll cover the other methods in a future video. How do you write a Docker file? A Docker file is a text file with a series of commands in it. Create a new folder, move into it, and create a file called Dockerfile with these contents. You begin the Docker file by defining the base image with the from command. This example uses a node.js image, so you have access to the node.js binaries. The official node.js image is called node. Next, you declare the maintainer with the label command. In this case, I'll just enter my email, but you can replace this with your own email since it's your Docker file now. This line isn't required to make a working Docker file, but it's good practice to include it. At this point, the build has inherited the state of the node container and you're ready to work on top of it. Next, you can clone the to-do app code from Docker in practice with a run command. This uses the specified command to retrieve the code for the application, running Git within the container. Git is installed inside the base node image in this case, but you can't take this kind of thing for granted. Now you move to the new clone directory with a workdir command. Not only does this change directories within the build context, but the last workdir command determines which directory you're in by default when you start up your container from your built image. Next, you run the Node Package Manager's install command, npm. This will set up the dependencies for your application. You aren't interested in the output in this example, so you redirect it to dev null. Because port 8000 is used by the application, you use the expose command to tell Docker that containers from the built image should listen on this port. Finally, you use the command to tell Docker which command will be run when the container is started up. This simple example illustrates several key features of Docker and Docker files. A Docker file is a simple sequence of a limited set of commands run in strict order. It affects the files and metadata of the resulting image. Here, the run command affects the file system by checking out and installing applications, and the expose command and workdir commands affect the metadata of the image. How do you build a Docker image? You've defined your Docker file's build steps. Now you're going to build the Docker image from it by typing docker build period. You now have a Docker image with an image ID. It can be cumbersome to keep referring to this ID, so you can tag it for easier reference with docker tag, the image ID of your choice, and to-do app. You can now build your own copy of a Docker image from a Docker file, reproducing an environment defined by someone else. So now we're to running a Docker container. You've built and tagged your Docker image. Now you can run it as a container. Use docker run-i-t-p 8000:8000 name example1 to-do app to start the container. The docker run subcommand starts the container. The -i option is short for --interactive, which keeps standard in open even if it isn't attached. The -t option is short for --tty, which allocates a pseudo TTY that allows you to communicate with the terminal in the Docker container. The -p option maps the container's port 8000 to the port 8000 on the host machine, so you should now be able to navigate with your browser to http://localhost:8000 to view the application. Finally, the --name option gives the container a unique name, and the last argument is the image. Once your container is started, press Ctrl+C to terminate the process and the container. Run docker ps-a to show all containers, including stop containers. Note that each container has its own container ID and status, analogous to a process. If status is exited, but you can restart it. Use docker start example1 to restart this container, this time in the background. Run the docker ps command again to see all running containers. After you do, notice how the status has changed to up, and the port mapping from the container to host machine is now displayed. Run docker diff example1 to see which files have been affected since the image was instantiated as a container. In this case, the to-do directory has been changed, which is marked with a C, and the other listed files have been added, which is marked with an A. No files have been deleted, which is the other possibility, and they would be marked with a D. As you can see, the fact that Docker contains your environment means that you can treat it as an entity on which actions can be predictably performed. This gives Docker its breadth of power. You can affect the software lifecycle from development to production and maintenance. These changes are what we're going to cover, and I'll show you in practical terms what can be done with Docker. Next, you're going to learn about layering, another key concept in Docker. So what is layering? Docker layering helps you manage a big problem that arises when you use containers at scale. Imagine what would happen if you started up hundreds or even thousands of the to-do app, and each of those required a copy of the files to be stored somewhere. As you can imagine, disk space would run out pretty quickly. By default, Docker internally uses a copy on write mechanism to reduce the amount of disk space required. Whenever a running container needs to write to a file, it records the change by copying the item to a new area of disk. When a Docker commit is performed, this new area of disk is frozen and recorded as a layer with its own identifier. This partly explains how Docker containers can start up so quickly. They have nothing to copy because all the data has already been stored as the image. Copy on write is a standard optimization strategy used in computing. When you create a new object of any type from a template, rather than copying the entire set of data required, you only copy data over when it's changed. Depending on the use case, this can save considerable resources. In the to-do app that you've built here, there are 3 layers you're interested in. The base Ubuntu layer contains the standard base packages for the distribution. The node image was layered on top of that to provide the node.js binaries and files. Then our to-do apps files were layered on top of that to provide the to-do functionality we exposed on port 8000. The layers are static, so if you need to change anything in a higher layer, you can just build on top of the image you wish to take as a reference. In the To-Do app, you built from the publicly available node image, which was built on an Ubuntu image, and you layered your changes on top. All three layers can be shared across multiple running containers, much as a shared library can be shared in memory across multiple running processes. This is a vital feature for operations, allowing you to run numerous containers based on different images on host machines without running out of disk space. Imagine that you're running the To-Do app as a live service for paying customers. You can scale up your offering to a large number of users. If you're developing, you can spin up many different environments on your local machine at once. If you're moving through tests, you can run many more tests simultaneously and far more quickly than before. All these things are made possible by layering. By building and running an application with Docker, you've begun to see the power that Docker can bring to your workflow. Reproducing and sharing specific environments and being able to land these in various places gives you both flexibility and control over development. In summary, Docker is an attempt to do for software what containerization did for the shipping industry by reducing the cost of local differences through standardization. Some of the uses for Docker include prototyping software, packaging software, reducing the cost of testing and debugging environments, and enabling DevOps practices such as continuous delivery, or CD. You can build and run a Docker application from a Docker file using the commands docker build and docker run. A Docker image is a template for a running container. This is similar to the difference between a program executable and a running process. Changes to running containers can be committed and tagged as new images. Finally, remember that images are created from a layered file system, which reduces the space used by Docker images on your host. Thank you for taking the time to watch, and please reach out if you have any questions.